All right, proof number 2. We've got the given information that WY is congruent to XZ. Okay. Remember, if two things are congruent, we can automatically say that the two lengths are equal to each other. So in the second step here, the second statement, we're going to say that the length of WY is equal to the length of XZ. Okay, and that is by the definition of congruency. Okay, and then based on that given information, there's not a whole lot more we can go off of. So this is when now we're going to look at the picture. Okay, and if we look at the picture, we've got quite a few line segments here. But one of the things that we're going to say is that line segment, this part WX plus the part XY, that is equal to the whole segment of WY. Okay, because we know something about WY. And then we're also going to look at XY plus YZ, and that equals XZ. Okay, because again, we know something about XZ. Okay, both of those reasons for statements 3 and 4 are, that is the segment addition postulate. Okay, now we know something about WY, we know something about XZ. Okay, so we are going to substitute these addition statements in, like in this second statement here. Okay, so we can say that WX plus XY is equal to XY plus YZ. Okay, WX plus XY represented WY. XY plus YZ represented XZ. Okay, so we just substituted those two addition expressions in for the parts that they represented. Okay, now step 6 here. If we look, both the left and the right side of this equation have an XY, and so we can subtract XY from both sides, and that will give us WX equals YZ. Okay, and again, that's because we are subtracting an XY from both sides. And then remember, if two lengths are equal, we can say that the two parts are congruent. So since WX equals YZ, those lengths equal each other, we can say that they are congruent to each other, that the line segments are congruent to each other. Okay, and remember, our last statement should always be what we're trying to prove.